Hello, welcome to one of our last video notes of the year, properties of logarithms. So last class we learned about logarithms, and hopefully we got an understanding of the pattern here that a logarithm is just equal to the exponent, and we see that relationship. If I have log base b of base b of a is equal to x, then if I were to translate that to exponential notation, remember it's equal to the exponent, so this x would be the exponent, b is still the base, so b to the x is equal to a. And that's a relationship between logarithms and exponents, and it's a very useful relationship because we're going to want to sometimes go back and forth depending on solving what's easier to solve, either logarithmically or exponentially. So these are some properties of logarithms that we're going to use. They're going to be very important in terms of your Eastern final. They have a ginormous logarithm problem that comes from this, and of course on your exam for us. So log base b of b to the x is equal to x. So this is a property that basically says if you have the same, let's say, let's just throw numbers in here. So if we have log base 3 of 3 to the 4th power, that's just equal to 4. You can kind of think of it as like the logs are canceling out and you're left with that exponent. So that's why when you have log base b of b to the 1st, it's just 1, and log base b of 1 is just equal to 0. And the reason is, if we translate this to exponential notation, b to the 0 power is equal to 1. Well, that's a fact. Anything to the 0 power is equal to 1. Okay, here's a very important rule. Both of these are going to have to use these. This is expanding and condensing. So we say addition properties and subtraction properties, but they're actually very similar to the exponential properties. So remember, if I have a to the n times a to the m, it's equal to a to the n plus m. Well, that's the idea here. If I have log base b of p times q, or pq, it's the same thing as saying log base b of p plus log base b of q. What a lot of students forget sometimes is to write the log for both of these. Sometimes they'll just write log base b of p plus q. It's like, no, you have to include the log of both of these, just like we have the a written here, the single a, but here we have the double a for the exponents. Over here, it's the same thing with subtraction. P divided by q is log base b of p minus log base b of q. And again, we know that rule. A to the n over a to the m is equal to a to the n minus m. So again, these are very closely related to exponent rules. Log base b of p to the n is equal to n times log base b of p. This is such an important rule. This is pretty much why we have logarithms to begin with, because it's a way to solve for that exponent, for that variable in the exponent, because it takes the exponent and brings it down in front. Log base b of x, log base b to the x log base b of p is equal to b to the x log base b of p to the x is equal to p to the x. This is kind of like a weird rule. I wouldn't worry about this one too much, but you see here that if you're raising a base to a log of the same base, they just pretty much cancel each other out and you're left with whatever's remaining. In this case, the p to the x. So the way they explain it is the base raised to the log exponent with same base is the input of the log. And number 6 used to be a huge formula when I was in high school because our calculators weren't able to do what yours are able to do. And that's a change of base formula. You're still going to need to know this, but now you guys have a feature in your calculators where you can put a box here for the logarithm and a box here for the input. So a box for the base and a box for the input. But back in the day, we didn't have that, and so we needed to use this change of base formula. Plus, you're going to use it for some other things. So log base a of x is equal to log base b of x over log base b of a. This is kind of confusing the way it's written, so let me just say we can only evaluate beforehand anyways log base 10, which we would call common log, and log base e, which we would call natural log, or ln. But if you have another base, let's say it's called base 3, and you have a number here that's not of the power of 3, Before, it was really hard to evaluate that. So we use this change of base formula to evaluate it using bases that we know work for us. So the way it works is we would pick a base we know, let's say common log, so log 10, and we would just say log 7 divided by log 3, right? And that's the change of base formula. So that we don't have to worry about log base 3 because we didn't know how to evaluate it. Again, now you do because you have the technology, but back in the day, we didn't have that technology, so we had to use the change of base formula. All right, so let's get a little practice here. I'm going to go a little faster through these just because you can rewind and I want to get to some of the challenging problems, and I want to make sure that I keep it under 30, which I know that you guys like. So, 1 second here. So let's talk about this. So log base 4 of 4. Well, remember, it's like saying it's 4 to the first power. So it's the same. We have the same base, log base 4, and this is the exponent base, right? So it's going to be equal to the exponent, which is 1. Okay. Log base 6 of 6 is 1. Natural log of e. Remember, natural log is the same thing as saying log base e. So what this is saying is log base e of e to the first, which is just 1. Okay, and all these are 0. Anytime you have the logarithm of 1, we know that it has to equal to 0 because that's the only exponent that allows you to get 1. Anything raised to the 0 power is 1. In other words, if we're translating this, it's basically saying 3 to the first power is 1, which is true. And for these, you're looking at the exponent because all these are the same base. Remember, log, if it just says log with no number underneath it, it's called common log, and it's really log base 10. So when you see log 10, it's common log base 10 of 10, so it's just equal to the exponent. Okay, over here, we're going to use these logs here, log base 6 of 9 plus log base 6 of x. And, you know, they're giving us the hint here. They're saying use this rule, but the rule goes backwards and forwards, so I can condense this and I can rewrite this as log base 6 of 9x, or log base 7 of 2 plus log base 7 of 5 plus log base 7 of y. These are all the same bases, and so since it's addition the entire time, I can rewrite this as a single log base 7 of 2 times 5 times y, or log base 7 of 10y. All right, b, right, same base, I'm adding them, which means I can condense it to a single log. So that's going to be x times 1 plus x with a single logarithm. The division works the exact same way. So subtraction, I'm just writing it as a division problem. So log, oh, this is base 8, so it can't do anything there. So that was, I think we messed up there. So that's just log base 2 of 24 minus log base 8 of z. You can't do anything with that. All right, going here, these you can. Both have a base 3, so it's just log base 3 of 14 divided by 2, which is log base 3 of 7. And again here, subtraction, the same logs, same base, so I'm able to rewrite this as a natural log of x over x minus 2. And now with these combos here, this is again something you're going to have to get really used to, is we go in order from left to right. So first, if you want to break it up into chunks here, let's first handle this. So that would be log base 4 of 5 divided by 2 plus log base 4 of a minus log base 4 of b. And then we'll handle this chunk. So that's as a. Log base 4 of a times 5 over 2 minus log base 4 of b. And then we'll handle this chunk. Remember, it's the division. Subtraction is just division. So this is going to be log base 4 of a times 5 over 2b. And that's what the final answer is. So log base 4 of a times 5 over b times 2, or 2b. Okay, same thing here, just kind of going in chunks from left to right. It's plus, so it's going to be log base 5 of 12 minus log base 5 of 3 minus log base 5 of d. Then we'll do this chunk. Log base 5 of 4, 12 divided by 3, minus log base 5 of d. And then the last thing is a final answer. That's log base 5 of 4 divided by d. Okay, now I know some of you guys could go a little faster. You guys could probably kind of do it all in once. You would notice, like, okay, 6 times 2 divided by 3 divided by d. But for the ones who need a little bit of help, I try to slow it down there so you can break it up into chunks. Okay, and we could also go in the other direction. We could separate it. This is just log base 6 of 3 plus log base 6 of x. Notice I wrote the log both times. Don't forget that. Natural log of 5 plus natural log of y. Log base 10, if there's no number there, it's base 10, so we call it common log. So common log 7 minus common log z. I'll only use the cursive for natural log. Log base 2 of a divided by 6 is just log base 2 of a minus log base 2 of 6. And over here, we have multiple things going on, right? So we could separate them right away as a subtraction problem. So log base 5 of 2x minus log base 5 of 3y. But you're going to have to separate them more because it's times and times. So we'll have to bring it to log base 5 of 2 plus log base 5 of x minus log base 5 of 3, I'm going to put this in parentheses, plus log base 5 of y. But if you think about it, it's minus minus, right? Because this whole thing is one problem with a minus sign out here. So when you distribute that negative sign, it should be log base 5 of 2 plus log base 5 of x minus log base 5 of 3 minus log base 5 of y. All right, so the same thing here. We know that it's in the denominator, so it's going to be minus minus. So I guess if you want to skip steps, you could just say log base 7 of x plus log base 7 of parentheses 3 minus x minus log base 7 of 5 minus log base 7 of y. Okay, over here, we're using this property. Again, it's such a useful property. Like example 4, if you remember anything from these notes, it would be example 3, the condensing and expanding, and example 4, which is basically saying you take what's in the exponent here and you just move it in front. Okay, so that's 5 log base 4 of x. Or you go into reverse, log base 2 of a to the 5th. Or you bring it down, 3x common log of 2. Or you go in reverse, log base 7 of 9 to the 5b. Or you bring it down, not the 3, just the x minus 1. X minus 1 in parentheses of log base 8 of 3. Or you bring it up, natural log of 3 raised to the x minus 5 power. Right, and this is just basically canceling. I mean, I know that's not the correct term, but that's one way of thinking about it. So cancel it, 7. If they see the same base, x, same base, a to the 3rd. Right, now here, we're going to use the change of base formula. And when they say log b here as the example, what they're really asking you to use is something that you guys know. So you're going to use either natural log or common log. You're actually the exact same answer, which is kind of the neat thing about this. It's like you think like, oh, if I use natural log, I'm going to get a different answer than if I use common log. No, you get the exact same answer. That's the beauty of this formula. So log base 5 of 16, again, your calculators can evaluate it, but most in the past they couldn't. So now we'll go ahead and write this as, I'll say natural log of 16 over natural log of 5. That's the change of base formula. Log base 3 of 5. Okay, well, let's use log this time. Log 5 divided by log 3. Natural log of 7, base 7 of 3. Let's use natural log. Natural log of 3 over natural log of 7. All right, so that's how the change of base formula works. You're going to either use log or natural log. All right, so now They want you to they want to challenge you guys at not use calculators, which I totally can understand. But if you want to use calculators, it's fine. So log base 10 of 50 plus log base 10 of 2. So this will be log base 10 of 50 times 2, which is 100. And remember, 100 is 10 squared. So this is the same thing as saying log base 10 of 10 squared. And based on those properties, I know that the answer is just 2. Log base 3 of 54 minus log base 3 of 2. That's just really log base 3 of 54 divided by 2, which is 27. But remember, 27 is 3 to the third power. So this is log base 3 of 3 to the third, which is just 3 as the final answer. 5, you have your base here of 5 to log base 5 of 3 minus log base 5 of 9. Well, let's first combine these. So this would be a 5 log base 5 of 3 over 9. And remember, if you have the same bases here, these cancel out, and you're just left with 3 over 9, or 1/3. Same thing here with the 4, it's times, because it's a plus. So this is just 4 log base 4 of 64. And 64, well, you don't have to do anything else, because this 4 and this log base 4 cancel, and the answer is just 64. Over here, let's rewrite this with the radicals. We know there's a relationship between radicals and exponents. So I could just rewrite this log base 5 of 125 to the 1/3 power. Now 125 is 5 to the third power. So this is log base 5 of 5 to the third raised to the 1/3. And by exponent rules, this is log base 5 of 5, because 3 times 1/3 is 1. Or the answer is just 1. I know, through all that, it just becomes 1. Same thing here. Log base 2 of 16 to the 1/5 power. But we know something about 16. It's a power of 2. It's 2 to the 4th power. So this is log base 2 of 2 to the 4th raised to the 1/5 power, or log base 2 of 2 to the 4/5 power. But since you have the same base, this cancel, and you're left with just 4/5. Same thing here with the natural log. So this is natural log of e to the 7/5 power. E and natural log they cancel out, and it's 7/5. I love these next few questions. These are change of base, but with a little twist. So I have log base 3 of 7 times log base 3 of 9. Well, using the change of base formula, because otherwise they have nothing in common, this just becomes, let's say, we'll use natural log. Natural log of 7 over natural log of 3 times natural log of 9 over natural log of 7. And we notice, hopefully you notice, that we have the same thing on the numerator and denominator, so they divide out to 1, and now I'm left with natural log of 9 over natural log of 3, and I can kind of recombine them here, and I could get natural log of 3 squared over natural log of 3, and using the formula, that real power property that allows me to bring the exponent in front, this becomes 2 over natural log of 3 over natural log of 3, which is just 2. I know it's crazy. It's like I'm speaking another language here, but you guys will get this if you just you can rewatch this and kind of watch what I did here. All right. So let's take a look at this next one. This time I'll use common log. So common log of 13 over common log of 2 times common log of 32 over common log of 13. These cancel out, and I'm left with log of 32 over log of 2. But I know that 32 is a power of 2. It's 2 to the 5th power. So this is log of 2 to the 5th over log of 2. I could bring this 5 out in front, and now it's 5 log 2 over log 2, which is just 5. So this next one here, same idea. I'll write small. So log 5 over log 4, log 64 to the x over log 4, 5. These 5's cancel. 64 is 4 to the 3rd power. So this becomes log of 4 to the 3x power over log 4. The 3x comes out in front, and it's just 3x. Okay, so now some are different logarithms here with the twist. The twist is that you're going to recognize some of them have the same base. So for example, log base 5 of 25 plus log base 5 of x. But 25 is just 5 squared. So log base 5 of 5 squared plus log base 5 of x. And that's just 2. So it's 2 plus log base 5 of x. Over here, natural log of x minus 8 minus natural log of e to the 2x. Remember, these are the same, so this becomes natural log of x minus 8 minus 2x. And I know it's tempting to combine them, but you can't. You can't separate the natural log from that. And then again, this is more like you're gonna see something just like this on the test. A lot of separation here. So common log x plus common log of x plus 3 minus common log x plus 5 to the 8th. But I can bring that 8 out in front. So log x plus log x plus 3 minus 8 log x plus 5. So this is called expanding. You're rewriting it as long as you possibly can rewrite something. And this is condensing. So you're writing it as a single logarithm, which means you're trying to condense it as small as you possibly can. So we'll start with these numbers in front and write them as exponents. So this is log base 3 of u to the 6th plus log base 3 of v to the 5th. And since it's the same base and we're adding them, I'm allowed to rewrite it as a single logarithm, log base b of u to the 6th times v to the 5th. Over here, you could deal with this exponent here. I don't think it really makes a big difference, but this would just be, since it's a subtraction, log base 7 of the square root of x divided by x to the 11th power. Here, a lot of stuff going on. You see these numbers in front. Just go ahead and make those exponents. So log base a of 7x to the 6th to the 3rd power minus log base a of 5x plus 19 to the 1/8th power, and then rewrite it as a single logarithm with division, log base a of 7x to the 6th raised to the 3rd power over 5 plus 19 raised to the 1/8th power. And the last thing here, I love these kind of problems. They're like riddles, like I think picture the Enigma machine in World War II, where you have to rewrite it in a separate language here. So they're saying log base 7 of 2 is a and log base 7 of 3 is b, and you're going to write these in terms of a or b. So it's not always easy to decipher when you look at it at first, but look at it, for example, this one. I know that 6 is a product of 2 times 3, so I can rewrite this as log base 7 of 2 plus log base 7 of 3, because 6 is equal to 2 times 3. And now look at this. Here's your A, here's your B, so the answer is just A plus B. Log base 7 of 8, that's log base 7 of 2 to the 3rd power, and log base 7 of 2 is a, so this is just a to the 3rd power. Or, probably even go further here, I can't write it like that, but put the 3 in front. That's 3 log base 7 of 2, and log base 7 of 2 is just a, so it's 3a. Over here, log base 7 of 4 minus log base 7 of 27, and 4 is 2 squared, so log base 7 of 2 squared. 27 is 3 cubed, log base 7 of 3 cubed. Bring those numbers out in front. So this is 2a minus 3b. Okay, so same idea here. I think we decided years ago we're just going to kind of skip this section. So we'll do example 5 here. I'll just separate it, and you guys can do it for fun later. So log base 3 of 4 times 3, That's log base 3 of 4 plus log base 3 of 3. So log base 3 of 4 is just a, so it's just a plus 1. Over here, log base 3 of 100. Well, 100, it's not a power of 5, but 4 times 25 works, right? So that's log base 3 of 4 plus log base 3 of 25. 25 is a power of 5. Log base 3 of 4 is a. So this is log base 3 of 4 plus log base 3 of 5 squared. That 2 comes out in front, and this will be a plus 2b. And lastly, I know sometimes like we do it like we want to separate it, but 30 divided by 6 is just 5. So this is log base 3 of 5, which is just b. And over here, we're just going to show one of these. Express y as a function of x. The constant c is a positive number. So we're trying to get y like by itself. And so I'm going to try to condense into a single logarithm. Natural log of y is equal to the natural log of 6x times c. And when you have the natural log on both sides, we can do something like, it's kind of like, think of it as raising both sides, using e to the, on both sides. So it's e to the natural log of y equals e to the natural log of 6x plus c. And that gets rid of the natural log, and we're left with just y is equal to 6xc. It's kind of like that exponent rule where you have a to the m is equal to a to the n, then m must equal n. And that's the same idea here, right? So if you have the natural log on both sides, it's going to be the exact same thing. Or, for example, for b, if I just raise both sides to e here, technically I could get y by itself by saying y minus 3 is equal to e to the negative 5x plus the natural log of c, and just add 3 to both sides. And I've done the task by getting y by itself. And a natural log of c, that said c is a positive number, so this is just a number. I know it looks weird, but that's just a number. Okay. All right, We'll stop here. Okay, great work. Remember, rewind, ask questions in class, and we'll see you guys after the weekend, long weekend.